Hi, in this video we're going to learn how to use the normal calculator. The normal statistical calculator is for the normal probability model that is introduced in chapter 7 of your content in Pearson. So I'm going to go to the Pearson assignment item and go to Lab 7, Quiz 7, where you see the normal and other continuous models. Besides elaborating on what the normal model is from a practical point of view by using STATCRUNCH, stat calculators normal, I encourage you to look at the notes on chapter 7 that I've posted on Canvas, where the normal model is presented and a lot of different applications of the normal model are used. And I'm going to also be building a whiteboard situation here on what the normal model is. So what is the normal probability model? The normal probability model is for variables that are random. And you say that a particular variable is normal when the following aspects are true. So x has to be a variable that takes on continuous values, not discrete countable values. So there's infinitely many possibilities when you have a continuous range of values, and from an arithmetic point of view, you can't really count all the possibilities. They're infinitely many. And so what we count will be relative subranges to this larger range, and that's how we manage to count fractions of infinity with other smaller infinities, so to speak. So x is going to be a continuous values variable. This means that our best chance we have at positing and then managing what the values of x are in terms of measuring probabilities is by looking at subranges of values that are smaller infinities than the overall range of possibilities. So x will be a continuous valued random variable. X will have a shape that is referred to as bell-shaped sometimes. That is better defined as perfectly unimodal and symmetric. And so whenever we're looking at a variable x that has values that are normal, we would take the variable x and we would say, okay, this is the average value. The average value is the likeliest. And then the probabilities of seeing values below average decline as values get smaller from average, and the probabilities also decline in a perfectly symmetrical manner, in a mirror image way from this value. And the mean, this is the Greek letter m here, the mean is the expected value of x. And then a very important characteristic of normals is defined as x follows the 68, 95, 99.7 rule, also known as the empirical rule. What that means is that if I shade an area of this curve such that I'm looking at an area that is this yellow zone here, so this yellow zone represents 68%, roughly 68% of the entire curve. And these limits here and here are roughly 1 standard deviation to the right and 1 standard deviation to the left. So 68% of the curve is in a range of 1 standard deviation above and below average. If I then add 1 more standard deviation, if I then go and look at this region in the highlighted blue, empty, that particular area constitutes roughly 95% of all values of x lie within plus minus 2 standard deviations from the mean. In other words, if I go and look at this limit to this limit, I go this direction, and I look at this direction in blue, that is 2 standard deviations above average and 2 standard deviations below average. And last but not least, if I'm looking at a region that is includes this purple region, the purple region encompasses the blue region and the yellow region. So that is a region of roughly 99.7% of all possible values of x lie within plus or minus 3 standard deviations of x. In other words, if I go and extend to the tips of the purple arrows, I'm going to be looking at 3 standard deviations as opposed to 2 standard deviations. Those would be minus 3 standard deviations. And this line would be plus 3 standard deviations. So the 68, 95, 99.7 rule helps us connect values of x with percentages of occurrences or probabilities of x. Let's look at an example. Suppose I have a normal population, a population measured by their cholesterol, overall cholesterol level. Follows a model that we're going to call normal, with an average of 190, give or take 20. So how do I actually draw this model? The way I do that is I build a scale here. And in this scale, X is the level of cholesterol, which is usually measured in milligrams per deciliter of blood. And then I'm going to draw a bell curve. Sorry that my drawing skills are not necessarily all that great. Perfect. And then over here, I'm going to start this at 130. 150. 170. 190. 210. 230. And 250. And that is essentially, if we're looking at a statistical scale, if we're looking at z-scores, be -3 deviations from the mean, -2 deviations from the mean, -1 deviation, 1 deviation below the mean. This would be the mean. And then 210 represents 1 standard deviation above average, 2 deviations above average, 3 deviations above average. Okay, so people who have a z-score of 3 are people who have really high cholesterol levels. People who have a 130, 150 have super low cholesterol levels. The usual cholesterol readings are 170 to 210. So those are people who are sort of like in the normal range. And then some people have too much cholesterol, like 230, 220, 240. Some people have too little cholesterol, 160, 140 and whatnot. So both extremes can be indicative of different kinds of conditions that are not healthy. And so we would call the 170 to 10 the normal range, the usual. Okay. So this is the usual levels or normal levels. And then we could then qualify these people here as unusual and these people here as unusual. And these people who are in these fringes here and there are between 2 and 3 deviations from the mean. Those people could be labeled as very unusual. And there are people who are just outliers. And so we would call these people here and these people on the bottom side here extreme values or outliers. So these are low outliers. These are high outliers. Notice how, depending on how many standard differences from the average people are located, they're extremely low in probability and extremely high or low in value, and thus they're called outliers. Okay, so outliers are extremely high and or low values, and they are very infrequent. Very infrequent, low probability. How do we use the normal model in StatCrunch? The way we use the normal model in StatCrunch is we open the calculator by going stat calculators normal. And then this normal calculator, notice, goes up to 3 standard deviations to the right and to the left of the center. It opens in what's called the standard mode, which is mean 0, deviation 1. It opens in units of z-scores. And so if I want to know what the probability is of observing some numeric value that is 2 standard deviations above the average, the red zone indicates that that will have a probability of 2.2%. If something has a probability of at least 1 deviation above average, that's 15%. So I can measure extreme values, but I can also measure central values by measuring that within 1 deviation from the mean, I see about 68%. If I change this to 2 deviations from the mean, I observe about 95% of values. If I go 3 deviations from the mean, like prescribed by the empirical rule, that's 99.7% of values. And there's very little left out on the extremes beyond that. There are very few exceptional outliers. There's almost no outliers, so that's why it's called a normal model, because almost everything that happens is normal, is usual, is high enough in frequency that almost everything can be captured or seen by the normal model, as long as you operate in a framework where the values are represented by properly as unimodal symmetric in shape, where the mean and the median are close in value and you see virtually no skewness of any kind. And that's what a normal calculator looks like. Now, I have really access to an infinite number of these normal calculators, because once I adopt a mean of any value, like for example, I could have a 190 mean and a deviation of 20, like in my cholesterol problem. And say I'm interested in 95% of people, you'll see that this 95% in red represents 2 deviations from the mean. Let me demonstrate that by clicking on this new button that appeared up here called the 68, 95, 99.7 ticks. What's going to happen is that instead of the scale being in 40 units or 20 units from the center at 200 or whatever, well, it's not even centered here, the center, I'll change the tick. When you click on this blue button, the tick marks occur, the central one at the mean, and then you'll see 3 tick marks to the left and 3 tick marks to the right. There you go. So that shows you the full scale of the normal range of possible, of viewable or cholesterol readings that one would expect to see, and how things can vary from that expectation in population in question. So notice how these models are very useful. They tell you 95% of people are going to get a 150 to a 230 in their blood readings of cholesterol in a population with a mean of 190 and a deviation of 20. So once I have the mean and the standard deviation of a normal model, I pretty much have a complete description of that entire set of possibilities, which is what a probability model should be capable of giving us, a complete description of something. So you can use the between mode, you can use the standard mode, you can say what's the probability that people will have cholesterol readings exceeding 220, because maybe higher than 220 could put you at risk of a heart attack. And so when people take a blood test and they find cholesterol levels on those blood tests of higher than 220, that's going to happen about 6 or 7% with 6 or 7% probability. And so now people can write an article and say 6.68% of Americans are at risk of a heart attack. That's what they mean by a statement like that. They mean that the population of people's cholesterol readings are described by some probability model, and that people who have heart attacks invariably tend to have really high cholesterol readings, and really high in this context means 220 or higher. And that's how the normal model, that's how risks and probabilities are measured. By establishing in either discrete or in continuous models the probabilities of bad things happening to people or high risk things happening to people, same thing. I hope that this video was helpful at learning how to use the normal calculator. If you have any questions about Lab 7 or Quiz 7, send them to me and I will put short video clips on how to use this calculator to help with your needs. And thank you for watching.